So we're past the pre-paving stuff. Now we're finally time to talk about what we're here to talk about, the construction. So we're going to talk mostly in the beginning about slip-form paving because it is the more complex and difficult to understand, but it's the most economical way of constructing concrete pavements of any significant scale. Now in the U.S., slip-form pavers are so readily available that we do everything that we can with them. And we do the smallest amount of hand placements possible. Now, it takes a while to get the contractor basis to be to that point where slip-form paving is so standard, but once you're to that point, you're producing very high volumes of concrete roadways, very, very uniformly, and at the lowest cost possible. So while I grab my agua sin gas, if anybody wants to write this down, I said it would be up here again. For those who weren't here for the first presentation start, all of the slides today are available at this website. It's a shared Google Drive, and I'm giving you the PowerPoints, not the PDFs. So anything you want to borrow and reuse or anything, it's readily available right there. So last presentation was about pre-paving. Now we're here to talk about paving. And there's a field reference for this as well. This is another document that I worked on while at ACPA. It's the primary reference for this next hour or so, the process of paving. Now after that, we're going to talk some about international paving practices. And you'll see that things aren't that different from place to place. I've got examples from Chile, from around South America, Central America, places as far away as South Africa, Kenya, Europe. All over the world, we're doing concrete pavement construction, and the general way by which we do it does not change that much. So we're past this point. We've started with whatever soil that God has blessed or cursed us with, possibly improved that or covered it up, or done something to get us to the point where we're ready to build the concrete pavement. So the first step to make that happen is producing the concrete. That starts with the person who is managing the stockpiles. A lot of the materials that we incorporate into the concrete, such as the cement and the admixtures, are very well controlled. They're in contained units. So they get measured out very, very uniformly and with a high degree of precision. The aggregate that we use, though, is generally just sitting outside. So it's someone's responsibility to work that material, to make sure it has a uniform moisture content, and to constantly supply enough of that aggregate into hoppers, which will then get pulled from and weighed during the batching operation. So this stockpile management, this moving around of materials and maintaining a uniform moisture content is the responsibility of the loader operator. So they're constantly checking the supply of these hoppers and supplying more coarse and fine, so rock and sand. That position, that one job in this grand scheme of pavement construction is so important that ACPA has developed with our Federal Highway Administration another free training on best practices for handling aggregates for concrete paving. It's that critical of a thing. We have to make sure there's no clay inside the aggregate. We have to make sure they're as clean as possible, that they're as uniform as far as the gradation goes, every little detail. Again, we're so far along in this process of the very expensive task of building roads that to have things go wrong at this point undermines the entire process. So these people that are doing this position need their own training. So once we feed the aggregate and cement and everything else into our batching operation, we're mixing the concrete. Consistency is our primary goal. Just like the uniformity of the support, we're looking for uniformity and consistency batch to batch and within a batch. That way the concrete that we place will respond the same way throughout the paving operation. There's been many instances where I've had to help troubleshoot challenges in the field which were nothing more than one batch being too wet compared to the others. And if that happens and you're dragging a texture, which we'll get to, you're dragging a texture across the surface of the concrete, and all of a sudden the concrete becomes very, very high slump or wet, the texture digs in deeper. So uniformity, consistency, that's what we're working towards. We have two primary means of mixing the concrete. On the top, we see a central mixed or portable batch plant. And when the volume of construction is high enough, we can transport these central mixed batch plants out into the field anywhere in the world. So we just have to get the materials to that plant, and that plant is close to the job site. That minimizes our transport or hauling distances. If we're close to a city, we can use truck mixed or ready mixed concrete, where the trucks themselves are doing the mixing of the concrete. But you can only transport that so far. And there are differences in the mixing operations themselves between trucks mixed and central mixed. Truck mixed, we're adding our water, our admixtures, our water reducers all up front. We save a little bit of water towards the end to apply right before we place it in the field. But we mix the water and the admixtures, then the aggregate and the cement kind of go in together, and at last we have some water at the very end. For central mixed, which we're mixing in, there's one drum right here. So it's just like the drum on the back of a ready mix truck, but much larger, so we can get higher production rates. Into that drum, we continuously mix water. It's not all up front or at the end. We add our admixtures and our water reducers, same as we would for truck mixed, and our aggregate and cementitious are similar, but the water's slowly going in through the whole process. When it comes to hauling or delivery, we want to have a uniform rate of delivery. Uniformity is the name of the game for the contractor. If everything is uniform, then that means there's no deviations from the norm. It's those deviations from the norm, we call them gremlins in the US, the little problems that happen that cost the contractor money. And that's their risk. So everything is as uniform as possible. When you have trucks queuing up like this, the concrete that's going to be delivered in this first truck is going to be different than the concrete in that last truck. And when it's ready-mix trucks delivering, they'll end up adding more water to the system to try to make the slump match, because that's what the inspector in the field is looking at, is slump more than anything. And that's time dependent. So this last truck gets there 30 minutes later than he should have, puts some more water into the system, gets the slump where the inspector is looking for it to be. But what he's done is change the water to cement ratio, which changes the strength of the concrete and its durability. That's non-uniformity in the process. So keeping things as uniform as possible gives us the best end result. Some methods of transport. If we're using central mixed concrete, so here's our drum disposing concrete right into this end dump truck, we're mixing very large volumes. So this end dump truck will just lift up, and concrete will come out the back. Now we've devised different methods of transport because of the limitations in construction in the field. If you're using an end dump truck, you either have to dump that right in front of the paving or have some other conveying device move it to the side to get it in front of the paving. If you use a side dump truck like we see here in the middle, it just dumps to the side instead of out the back end. Now we can have a haul road that goes in one direction. All the trucks will enter in, side dump, and continue on. The next truck comes in right behind it in the queue. So there's all these little logistical things based on space limitations that might change the contractor that wins the low bid because this contractor had this equipment. So it's not as simple as just letting the project. There's all these other parts that move. We might use an agitating truck, or an agitor for short. It's not a ready-mix truck, but it has paddle mixer in there. So there's a shaft that rotates and paddles off of that. That helps extend the transportation time, the delivery time, before that concrete starts to set up. Or we might use ready-mix trucks. Those are the most common that we see in the US. Now, generally, you have about 30 minutes to deliver and place the concrete. That's a pretty small window, especially when we're talking about very large projects. And if they're at any distance from a city, or if it's like it was this morning at 8 a.m. in Santiago and there's traffic. So those agitator paddles can extend that delivery time to about 90 minutes, as can the use of some retarding admixtures. They just slow down the hydration, give us more time to deliver. Delivery time also depends on the ambient temperature. You need to make sure you have enough trucks to supply the paving operation. So that's another one of those simple web tools that ACPA has. It's a rate of delivery calculator. So based on the forward speed of paving that you're intending to have, you need to match the supply of concrete to that, which is dependent on the thickness of the pavement and its width, and the volume of the delivery trucks themselves. One second. Presentation seems to have frozen. There we go. So ready mix trucks. This is both for mixing and delivery. But you have to be close enough to the ready mix batch plant for this to happen. So this is most common for streets and roads because those are the things that are near the city. We generally have about 90 minutes to deliver the concrete. We see a minimum number of revolutions specified around 70 and a max of about 300 typically. So the longer they are into that delivery window, the more they will mix it. There is a slump meter inside of the back of the ready mix truck, which gives the driver an estimate within about 13 millimeters of the slump of that concrete. Again, as with any slump test, this is quality control purposes only. This does not say that that concrete is a specific strength. All it says is this is the consistency of that concrete. So when the contractor receives ready mix trucks because they're not controlling that operation like they are with central mix, they get a batch ticket. It tells them what the proportions were of everything that's being delivered. So that's one fundamental difference. Central mix, contractors doing it all themselves. They're dealing with the material suppliers and they're purchasing rock and cement and everything else. They're mixing it themselves and they're constructing it themselves. They have full control of the entire process. Ready mix, there's an extra layer. There's the delivery of the ready mix and supply of it from the ready mix supplier, which adds another component of liability and whose fault is it when something goes wrong. So these batch tickets are some sort of evidence about what was delivered. The challenge is from the contractor's perspective, you never know how much water the ready mix driver added during transport. He may have seen that slump meter go down and it's not the slump they're looking for, and he's stuck in traffic. Just hop out, go to the back, add a little bit more water. Change the slump. That changes the water-cement ratio and the concrete's durability. So there are technologies in place now that can monitor all of the water additions. Just adds a little bit more cost to that process, but those exist. We generally allow one addition of water at the construction site where the contractor who's building the pavement can see it, and that requires another 30 revolutions of the drum in order to mix that in. So we've got our concrete mixed, transported. It's time to place it. One final note before we're finally to the point of concrete on the grade. It's right there. You can almost taste it or smell it. Right before we place the concrete, if we're building on top of an aggregate layer, and that aggregate layer is very dry, when we place the wet concrete on top of it, the aggregate will suck moisture from the concrete. That dries out the concrete right at that interface and changes its properties. So to try to combat that, when we have an aggregate layer, we will use a water truck to just spread some water onto the surface. We're not trying to saturate it. We're not trying to puddle water at all. We're just trying to satisfy the water demand, make it saturated, surface dry. Then when we place the concrete on top of it, there's no reason for the aggregate to suck any moisture from it. If we're paving on top of an asphalt layer, like we would with a bonded overlay on asphalt, or otherwise, we might use some other means of cooling the surface, like whitewashing it with curing compound. So access is important. Just like that helps us kind of dictate which type of delivery trucks we might use, it helps us dictate how we're going to get the concrete in front of the paving equipment. So here they're using in-dump trucks. They're delivering in one direction. This truck is not turning around to go back. Although in some projects, the contractors, I know of 3 cases in the US, where the contractors manufactured massive turntables. So the truck would drive onto it, they'd release the lever, and it would turn around and it'd go back the direction it came. That's how tight things were. So there are ways to get around this, but here he's driving forward, stopping in front of the equipment. The device in front of the equipment is called a placer spreader. And it has an arm that just comes down. The truck dumps the concrete. There's a conveyor that then brings the concrete up into the paving. The arm lifts up, the next truck can drive up. Arm down, concrete, convey. So it's a process that just cycles. Here we have a placer off to the side, which just has a conveyor, moves the concrete back and forth. What they're doing right here is bad. It's too high of a pile of concrete. It should be distributed as evenly as possible. Of course, with ready-mix trucks, we have chutes on the ready-mix trucks, or we can use a placer spreader here. So they have another conveyor system. Here's a photo of the string line having to be so far off to the side, way off to the left, and very high up, so that we can get our delivery vehicles underneath that, because there's nowhere else for the string line to go in this project. If we would have had the string line here, the haul road would have had too steep of a slope there, and it would have been dangerous. If necessary, and especially if you're not using dowel bars like in Chile, you can just deliver right in front of the paver. So the trucks can back up on one side, dump, move over, and just keep changing sides to stay out of each other's way logistically. If you're doing this, though, you have to ensure that the subbase is of a high enough strength to support those heavy truckloads, because a truck full of concrete is not light. If you're CBR 80 or plus here, that should be sufficient without rutting of the subbase. So here we have a case where we have pre-placed dowel bars on an asphalt subbase, so we can't just drive back into that. We have to deliver to the site. That's much of the reason why in the US we've developed so many different delivery methods, the widespread use of dowel bars. Again, if at any point you have any questions, it's going to be difficult to go back 60 slides, so speak up if you have any sort of questions. This is improper placement. When we have these mounds of concrete, the paver has to somehow push that to the side, distribute it. Now, I understand the translator spoke to me during the break. We call this a head of concrete right in front of the paver. That does not translate well. It's just the supply of concrete to the paving equipment itself. At the very end of today, we'll talk about innovations in construction. And one of the newest that we have is real-time smoothness. So everyone's always interested in building smooth roadways. With the concrete road, part of the challenge is once I partition that into joints, into slabs, and they start to curl, whose fault is the curl if that adds significantly to the roughness? Is it material selection, which is usually the owner specifying certain things? Is it the contractor and the construction environment? Is it the joint spacing itself? Because there is a relationship between joint spacing and roughness. So it becomes a very challenging problem to try to assign who's at risk there. So we've developed real-time smoothness, and immediately after the slip form pan, as soon as the contractor is done building that shape, we're getting a feedback of what the smoothness is as they've built it. And this is giving us new insight into the impact of construction processes. This, right here, is one of the biggest contributors to roughness in concrete pavement construction with slip-form equipment. Because the slip-form paver, it's running on tracks, Caterpillar tracks, it's moving forward. If it hits a big wall of concrete, it has to spread that. It pushes back against it, and it almost lifts the paver up just a little bit as it tries to fight over the top of that mound. It seems like a small thing, but every little thing like this, contractors are realizing makes a difference. We need to have that spread as uniformly as possible before it goes into the paver. A few notes on fixed form paving. Much less complex, and we'll get back to slip forming. Much less complex. You can use a roller screed like this, single tube. You can use a truss screed like this. In this particular example, we're doing the same thing. We're supplying the concrete. We have a wooden form on the outside here, existing concrete laying on the inside, supplying concrete, leveling it off, and somehow it's striking it smooth. The single tube screed, just a cylinder of steel, bring it out into the field. We fill it with water to give it some weight, so it pushes down on the concrete. And this gentleman on the background has a little throttle. And when he pulls that throttle, there's a little engine that spins it away from him. So it's constantly spinning in the other direction, which is why they're fighting to pull it back. You'll see that in the photos. This is a good, inexpensive way. This piece of equipment can transport anywhere. It's relatively lightweight when it's empty. This project right there was one I was on in Kansas. That's a roundabout right off the interstate. So we build some pretty high-speed roadways with fixed form paving. This looks to be on a bridge where they have that truss cantilevered out. Same idea. They're supplying concrete, they're spreading it around, leveling it out, and then striking it off. So these sort of screeds and trusses are good for very odd, complex areas. We would not be able to get a slip-form paver very easily into this space unless it's a sidewalk paver. It uses external vibration. There's either someone manually vibrating, I think we see that in the next slide, or this truss itself is shaking to provide some sort of vibrational energy that then makes the concrete temporarily fluid, so it consolidates itself. That's good up to a thickness of about 20 centimeters. There is larger equipment that we can use in a fixed form capacity. This example, it looks like they put in the curb and gutter, and they're using a bridge deck paver, a bidwell. So it's not slip forming, it's still using the gutters, those curbs, to contain the concrete when it's liquid. But this is a device that's common to see on top of bridge deck paving. Same idea. They're supplying concrete, and this moves back and forth with a roller screed to finish the surface. These are particularly useful if you have an arc or some odd shape you're trying to build into the system. Like I think one of the examples I have in South Africa, later, they have a road that they built with a negative curvature so that it serves as a ditch. They had so many problems with erosion in this mountainous area that they decided the traffic is so low, we can afford concrete, we're going to build it with concrete because that's erosion resistant compared to this emulsion asphalt and earth that we otherwise have. So they built a ditch into the road to help bring water down the mountainside. You can do that very easily with this. That'd be a little trickier to do with slip forming, just because the equipment's typically set up to go up. So fixed form paving limitations. You can pave up to about 15 meters wide, but there are some limitations once you get too wide. We're talking about relatively lightweight pieces of equipment. This steel cylinder, for example, if it becomes too wide, it's too slender. It'll start to bend down across that width. Slip-form pavers are very big, very strong, reinforced pieces of equipment that don't have any of those sort of problems once we become 15 meters or wider. So if the placement is large enough, the contractor will probably opt to use a slip form paver. That is what gets us the highest efficiency and the lowest cost possible. So fixed form, spreading the mixture. Just like with slip form, we want to spread it as evenly as possible across that width. So here we have a gentleman using a concrete rake. You can use a shovel, but not a pointed shovel, a flat-nosed shovel, square, to pick the concrete up and move it around. You can use concrete rakes like this, but keep the movement to a minimum. Anything we do that starts to segregate the system will tend to bring the fines to the surface and cause the coarser aggregate to go deeper into the concrete. But here they're spreading it uniformly. It's being delivered by a ready-mix truck. Here they have a triple tube screed, so those go in different directions. There's still someone spreading it out before they strike it off and finish it past that point. Consolidation, if necessary, if it becomes so thick, greater than about 20 centimeters, that the screed itself can't do the consolidation. This gentleman here has a backpack on which powers this spud vibrator. So it's just like the vibrators on the slip form equipment, except it's one single vibrator. So they will dip that in one location, move over, dip that in the next location, and always do it vertically so they have a constant zone of influence. If they go in at an angle at all, it causes, or drag the vibrator, it causes problems. So they do this vertically about 0.3 meters on center. And they have to make sure they get the edges more than anything to get consolidation right at that point. So this is a pretty liquid concrete compared to what we see in slip form paving. It's not taking that much work for one man with a concrete rake to just spread it out. You can see he's trying to go at it one-handed here. So he's got to pull pretty hard to get that thing moving in the direction that he wants it because it's spinning the other way, away from him. And that spinning just helps close off the surface. It's constantly dragging paste at the surface. Dowel bars and tie bars. Of course, if we have formwork, we have to somehow insert those through the form, or once the concrete is hard, drill into the concrete and then epoxy them in. It's much easier to do it when the concrete is plastic. So here's a steel form where we're inserting tie bars. This project is from an intersection in Indianapolis where they're using 3 different types of formwork in one project. I guess 4, really. They have the existing concrete. That's one type of form. We're paving right up against that. They have steel forms. Here's a straight wood form. And here's a flexible plastic form. They've got 2 thicknesses stacked on each other. So there's a lot of different approaches to getting it done. You just have to support the concrete. Once it becomes thick enough, and this section was about, what was that? Oh, it was a little over 20 centimeters if I had to guess from memory. Once you get tall enough and the concrete is relatively fluid, it has a high slump, there is a fair amount of formwork pressure. So you can't just use any forms. These have to actually be engineered and supported somehow, which is why these steel forms have such a wide footprint to help resist that bending over, that spinning over of it. Construction joints. So here's a header joint, as we call them. This is a system of plywood sheets in here where they've just drilled holes to help align the dowels. So they have underneath this tar paper, I think 3 vertical sheets of plywood. So the dowel bars stay perfectly aligned across there. This is the end result once they've removed that in a different spot. So a simple box, a simple jig developed by the contractor ensured full alignment in this case. For fixed form paving, thickness verification is a no-brainer. We set the forms, we know that's how thick we're going to build the pavement. There's not much question about that. For finishing, we can use a roller screed. We saw that, the single tube, triple tube. There's other devices, laser screeds, we'll see in a bit. We saw a bridge deck finisher. Any means we have to finish the concrete, to close it off, we can use. Can even just use a plywood or a wooden straight edge, a 2x4. Depending on the desired surface texture, there might or might not be subsequent finishing necessary. If you're going to create a very rough texture, there might not be concerned about how closed off the surface is necessarily. If you're trying to steel trowel the system, like you might in an industrial application, you want that surface to be as smooth and closed off as possible before they apply that finish. Generally, for roadways, the finishing is the same as it is for slip-form paving, with the straight edge and then some sort of texture after that. With forms, we have to remove the forms before we saw cut. Otherwise, we're going to saw cut into the forms, and the metal forms especially are not the cheapest things to have. So they remove the form work before saw cutting, and we'll catch up with where things go from there. But the texturing and curing, opening to traffic, all those sort of details for fixed form are the same as they are for slip form paving. So we'll get back to those. So we're picking up after the concrete delivery. Our slip form paver generally will have these placer spreaders at this point. You can just try to uniformly distribute the concrete with some conveyor or ready-mix truck, but in the US, we see more often than not a placer spreader ahead of the slip former. So this device is receiving the concrete and spreading it across the width. So the auger will be here instead of inside of the paver. Or the paver, in this particular case, they have the vibrators and an auger right above that, just for distribution at the surface. So we talked about this, that arm will drop and raise as necessary for trucks to pass. Or we can use conveyors. Some more examples. Sometimes we'll see these in asphalt operations too. Just conveying the concrete to move it around. So we're back to this point. We have our concrete head or constant supply of concrete out front. We're getting that there with the placer spreader or some other means. So the next thing we see is the auger. This is just a large horizontal screw. And there's someone operating the paving equipment, standing up top, always looking down the front, seeing what the supply looks like, looking around the back to see what the final product looks like, constantly keeping an eye on things. So it's this person's job to make sure all the parts within there go well. And they have a panel here which functions for a lot of different things, but the first thing is switches for these augers. And it's like an Archimedes screw, basically. We just spin it one direction, it pushes, spin it the other direction, and it pulls. And all we're trying to do is make sure we get concrete way out there into the corners. It sounds simple, but the paver is constantly moving forward. So this person's job is very stressful in that they're always looking there, looking out the back to see what the result was, coming back up front to make sure they push a little more concrete here or there. But their goal is to get a uniform supply of concrete across that width. Sometimes, it's not as common as the auger, we'll see a plow used. And we'll see that in one of the videos coming up. So instead of a screw turning and pushing concrete back and forth, this is a physical plow, pushes, comes back the other way. So past that point, again, some machines will have a strike-off, not all, to help manage the amount of concrete coming into the side forms themselves. But we next have the side forms and the vibrators, which work together. They're both necessary at that one point. Side forms just contain the concrete. Because when the vibrators go, when those are vibrating, the concrete becomes a fluid temporarily. So all these are doing is preventing that fluid from just spilling out the sides. So they're relatively rigid and strongly reinforced. If you look close at this photo, you can see one perspective of that edge slump. So remember, we're building it up taller than it needs to be. can see that perspective is a constant angle. This one kind of curves down to approach what it needed to be. I've got another photo that shows more of that edge slump in action, but that's right behind the pan. So the side forms contain the concrete, the vibrators as a system uniformly spaced with the frequency matching the paving speed even, temporarily fluidize the concrete. So we have our rolling head here. Concrete becomes a liquid, side forms hold it in. The standard paving equipment at this point comes with a device like this, because the challenge of vibrating is that if I'm moving along at this speed, my vibrators have to be very fast. If I slow down all of a sudden, if I have that same vibration, it segregates things. And then I have these vibrator trails. So the vibrating frequency has to match the speed of paving. Luckily, it's not that difficult of a thing to do with a relatively inexpensive piece of equipment. Vibrators are necessary anyway. This vibrator monitor system is just a supplement to that that makes everything work better and produces a more uniform system. So I guess to emphasize that point, these trails caused because the vibrator frequency was too high are entirely paced. So right where the vibrator was, it pushed all the aggregate away. So there's just lines of paste right down that road. So after that point, there may or may not be a tamper. Tamper just goes up and down. It helps just provide a little bit more consolidation. The last thing we'll have is a slip-form mold. But inside of this area right here, if we're using dowel bar insertion, that's when it happens. So I understand dowel bars aren't too common, but you might find this a novel idea if nothing else. So because of the limitations of delivery and the challenges with placing the steel ahead of time, it's also cost-driven. It's much easier to transport this pallet of round dowels stacked like that than dowels in big baskets. So we'll have dowels delivered in in bundles. Those get dropped at a regular frequency. On the slipform equipment then, there's a crane, which does nothing but picks up these baskets. Sorry, I keep saying baskets. Bundles of dowels. They're not in baskets. These bundles of dowels. It picks those up and brings them to where the dowel bar inserter is. So the slipform paving is constantly progressing. If we were to insert dowel bars at the same speed, we would have to drag it. So this piece of equipment, this part of the equipment, disengages from the slipformer. The paving equipment continues to move. This device stops, sits down on the surface, does its thing, and then picks up and catches up. So it has a system of pulleys and chains that make all of that happen. But when it's sitting on the surface, when it's temporarily disengaged, it's compressing, confining the surface just enough. Those bundles of dowels got cut. And there's a cartridge system that feeds them through. And when one of these passes by, a hole like this, it just drops in. So at that point, there's a dowel sitting in a hole. We then have this I-beam. It's a vibrating beam across the top. You can see part of it there. You can kind of see it here. That has forks, 4 of them attached to it. So these 4 forks go down, engage the round dowel. That beam vibrates, and it vibrates them down to the required depth. The required depth being this distance right here. From the point where the dowel will be fully engaged, the apex there, the top, to the full depth of insertion. So it's that simple. Supply the dowel bar, push it down, vibrate back out. So in the end, the system gets closed up due to the vibration, about like this. and it's enough that the pan then will close the rest of the way. It's a very cost-efficient way of building doweled concrete pavements. And we've found through experience that while there needs to be a very well-graded concrete for all of this sort of vibration and placement and vibration back out to work correctly, the alignment that we get with these systems is actually better than with baskets. With baskets, if there's any skew to that system at all, every single dowel is skewed. If it tilts forward at all. In this system, every single dowel is independent of the next. So you end up, if anything, with systematic errors of the third dowel in was always just a little too tweaked. And when it comes to the performance side of things, having one or two dowels in one joint misaligned does not cause any sort of locking or problem. It's when the whole system is skewed. So we found this to be a very cost-effective and efficient system. And in the US, that gives us direct access right in front of the paving, which we wouldn't otherwise have. So we've gone through the auger, all the other parts, the vibrators, the side forms. If you look close here, you'll see more of that edge slump happening. It looks a little bit thicker here than it is just a little bit past that. Happens very quickly. You can see here they're making a utility channel, the photo on the left. We can slip form very wide and thin too. We just change the mixture, we change the equipment, but we can make concrete stand up very, very tall. So this final form, this one that creates that angle, that pitch there, and that angle in, also pinches the concrete in just a little bit in every direction. So the side forms are pretty much parallel. This tapers in just enough to apply a final compression or final consolidation on the concrete. Any sort of cross slope or crown or anything else that we build into this is going to be built into it by the pan. When the concrete goes through the side forms and the vibrators, it's just fluid. We can't build a shape into it. So this is our final step of, if the concrete was found a uniform height because it was fluidized, the pan pushes it back up to create the crown in the middle. Confines it just enough for that to happen. So just like with dowel bar insertion, we can insert tie bars into the plastic concrete as well. It can be a relatively, and this is if we're paving more than one lane at a time, so we're paving 2 or more lanes at once. It can be relatively simple. The photo is on the bottom right. Someone would just sit in one of these chairs and manually place a tie bar into this wheel or this other cross device, and that just moves at the right speed with the paver to push it down into the pavement. And they get spaced correctly based on that circumference, that quarter circumference. That's a relatively low-tech way of doing it. If we're inserting tie bars into the side of the paving, the low-tech way of doing that is to just bend over and push one in. If that's a construction joint, someone can just physically bend over and push it in. And if you make the tie bars the same length as the tie bar spacing, once they push one in, they take the next one, set it next to that, rotate it, and push that one in. Because then the spacing matches the length. It's a very, very automated process then for labor to do that. This is a little bit more high tech. The benefit of this is that it confines the concrete. If you're pushing a piece of steel into a thickness of concrete, and that slab is confined on the bottom, when you push that in, it's going to push up on the concrete and leave a little tiny hump right at the surface. So this helps us prevent that action by confining the whole system. Here's the end result of this device dragging through the fresh concrete. So it's roughened up the surface some. It's not really that bad. That can be closed off in the finishing operations. It looks like here, yeah, that is happening right before finishing, it appears. No, this might be during a placer spreader. I don't know that piece is. Yeah, that is a placer spreader, 350. So that's happening before it's even going through the slip form mold. Now, the fluidization of the concrete with the tie bar inside of it will cause the tie bar to move around some and misalign some, but a tie bar is meant to lock the joint, so having it be somehow misaligned is not a problem. It's only going to better lock the joint, as long as it's not totally sideways. So some misalignment in tie bar location is okay, as long as you have concrete cover. We'll see a video of an even more automated method. It's comparable to the dowel bar inserters, but we have a device called the rocket launcher that just punches tie bars in at the right spot, one at a time. Sometimes we'll even use two-lift concrete pavement construction. We did this for a very long time in the early 1900s when jointed reinforced was common. We used fixed form paving. We built half the thickness with a spreader of some sort that sat down inside of the forms. We placed the steel fabric, and we finished constructing on top of that. So that's always the first question engineers have. How do you know the concrete will bond to the concrete? We've been doing it for 100 years, and it works, as long as it's still fresh. So once you get over that technical concern, this really opens the doors to a lot of different things. We're using it in the US more in pockets where we need to provide enhanced aggregate at the surface. So say we have a lot of limestone or aggregate that might polish easily. We can build the system to be 3/4 of that, and in the last quarter, we'll just pass by and use higher quality aggregate just to close off the surface, to cap the surface with a more durable material. So it could be economics driven, sustainability driven. We could just use fibers in one half the thickness and not the other half. We have opportunities to do a lot of different things when we functionally grade the system. In Europe, they'll use it to allow for an exposed aggregate surface. So for the same reason, they'll use the higher quality, lower or a finer gradation material at just the surface and not through the full thickness. This adds a lot of logistical problems, though, because you're supplying two different types of concrete to two different slip-form paving machines. So they have one placer spreader, one slip, two slip. This one has the rocket launchers on it, so I can see they're paving 3 lanes wide because they have 2 of those across that width. So they're building 3 slabs wide. And they got texture cure behind that. We want to avoid stopping the machine at all costs. It's much better to make very, very slow progress than to stop. If the system stops, you're going to introduce a little tiny hump at that point. It's nothing that you can do to stop it. It's just part of the process. So slowing down is good. Stopping altogether, it will inherently make some sort of roughness. So I mentioned that before. We have this real-time smoothness. That's these GSIs, Gameco Smoothness Indicators. That's one brand of that, right behind the paver, even before we've applied this burlap texture. So as soon as that concrete goes to the pan, the paving equipment knows exactly how smooth it is, and they can change the process to make it as smooth as possible in real time. For slip-form paving, our thickness verification, generally we will use someone on a bridge like this, an inspector, who just probes down into the pavement, wipes off the rod, waits till the next time, probes down, measures how deep it is. That's the easiest way to do it. Otherwise, you might use something like this magnetic imaging tool. The challenge here is that it requires pre-placement of metal sheets. So just little metal discs, throw those out into the field. We know where they are, use GPS, and then we can ping off of that, bounce off of it with magnetic imaging to know exactly how thick that concrete is. Or if necessary, if we have to do something destructive, we'll core the concrete. That in the US, we do that as little as possible, because now you've created some sort of non-uniformity, which is going to cause a difference in performance. So we prefer not to do that. When it comes to finishing, ideally, there is no finishing. The slip-form paving pan itself has created a perfectly closed surface. The materials were well graded enough to allow that to happen, and hopefully these people are just standing around. If necessary, though, we'll use this straight edge. Now this truck's out in the cornfields there, probably in Iowa, a little ways away, but you can see, based on the scale of this person, that straight edge is longer than one vehicle. So we're trying to get rid of that wavelength that's going to cause roughness in the ride by using this sort of straight edge. We don't want to add water at this point and overfinish the surface. If they're having problems closing the surface, something needs to change before that point. If the surface is not closed, we do have opportunities to fog the surface and curing and try to replenish the moisture that evaporates. But if you add a bunch of water at that point, the most common thing you'll see is a stick with a rag just duct taped to the top of it, someone walking around with a bucket, stick the rag into the bucket and bless the slab. I was raised Catholic, so stick the rag into the bucket and bless the slab. That's what they do. That adds water to the system. Again, changes the water to cement ratio, changes the properties of the concrete right at the surface. That's the point that is most critical. If you're going to have freeze-thaw damage, it's going to happen at the surface, not in the middle of the slab. So you don't want to do that. No adding of water at the surface. Some more photos of finishing, so we can see those. If you're paving several lanes wide, the handles will become very, very long on those straight edges. Now we see here a very large drop-off on that edge. That's got to be Oklahoma, judging by the color of the soil. Over here, I know that photo's from Iowa. I was on that project. If you look close at the edge, there's not that drop. Now, these are both low-volume roads, and that's why I put them in here together. When they're out in the farm fields, not that much traffic. They're both going to have dirt or gravel shoulders. What happens in service when you have this large drop-off, the dirt or the gravel starts to move away from the edge. Vehicles fall off of that drop-off if there's any sort of lip, 25 millimeters or more, and they're going very fast. They fall off of that edge, and a lot of the accidents that happen are from people overcorrecting. Instead of slowly guiding themselves back up at a point where the shoulder comes back up to the pavement, slowly, they just do that. They overreact, they go into other traffic, or they spin around and flip over. So we've devised this safety edge, which is just a fillet. So as the shoulder starts to move away from the concrete slab itself, that problem is less, because they have this nice transition back onto the slab. So we're seeing that applied. Our Federal Highway Administration was a big pusher in this on lower volume roadways. We're doing it on asphalt and concrete pavements. It's no harder for them to build this into the pavement than it is to make the edge perfectly straight. In fact, if that's the outside edge, having this helps with the slump. So it's minor detail, huge safety impacts. Texturing methods. We have a lot of different methods that we can use depending on what your requirements are, more for speed and friction than anything else. We will almost always start with the burlap drag. It's typical anywhere in the US, Canada, see it in Mexico too. So North America. This is just a sheet of burlap fabric. It's weighted down a little bit with some sand in there, and they're keeping it moist so it doesn't pull moisture from the surface. But this just drags across the surface and creates a nice micro texture. Next most abrasive, next step forward is probably a broom texture. It's just a stiff, bristled broom. Drag that back across the pavement, creates just a little bit rougher of a surface. So I had the burlap out front here. This is what the broom texture looks like behind it. The next most aggressive texture is an AstroTurf drag. So we take AstroTurf, the green artificial turf that you'll see on football fields. We'd flip it upside down, put some weight on top of it, and drag it across the surface. And it roughens up the surface just a little bit more than the other two methods so far. In the middle here, they've left out a blank out. It's a holiday so that they can stripe. And the stripes will stick to the concrete. So that's in between lanes. Next most aggressive is tining. We can do either transverse or longitudinal. Bottom left here, we see edge of pavement. We see tie bars. And this is on the texture and curing machine. It will stop, moves forward, it stops. It drops these tines and drags them across the width. The tines are just little metal bars spaced at whatever spacing is required by the specification. It might be uniform, it might be non-uniform. It all depends on what the owner is looking for. We see a lot less of this now and a lot more of this, longitudinal tining. Same idea, but instead of going back and forth and having to stop the equipment, we're constantly dragging it behind the paving. So the tines are in the direction of paving the whole way. Now, the original reason why we saw a lot of transverse tining, so against the direction of traffic, was that engineers had this idea that somehow the water would more easily flow out of the pavement system at the surface. Doesn't really make a difference. And that it would be a higher friction, because if you hit the brakes in your car, that's opposite the direction that you're traveling. So intuitively, you would think having the ridges that direction would help stop you. Also not the case.